This is lesson 10.7. Second to last lesson of the whole entire year. All right, warm up. Going over our 3 case scenarios of when secant lines intersect with either a chord or possibly a tangent line. So our 3 case scenarios of where they could intersect is inside the circle, on the circle, or outside the circle. And our rule for each is different. And I give you that little cheat sheet in your notes. You might have needed to use that. So 1 and 2, the intersection point was inside the circle. As a review, a secant line intersects the circle at 2 points. Okay? So this one's a secant line and a chord. The angle formed by these is exactly half the measure of the arc, the intercepted arc it forms, and the arc opposite. So here, that 95-degree angle is half of the arc it forms, which is x, that's what we're trying to find, and the sum of the opposite arc, which is 42 degrees. That's how you'd set this one up. To solve this, times both sides by 2, minus over the 42. I got x to be 148 degrees. All right, obviously you can check this answer by taking the sum of those, dividing it by 2, and you get 95. All right, number 2, similar, but I know this arc measure and this arc measure, and they're asking me to find this angle over here where I don't know that intercepted arc. I can't assume this is a diameter and that's 180. I can't assume that. And I don't know this one opposite of it either. So what I'm going to do is I'm probably going to call this maybe like y or something. I can find this angle by taking 1/2 the sum of 119 and 23. And I got 71. And then since these 2 angles lie on the same secant line, they're supplementary of each other. So x would just be 180 minus y. So x would be 109 for that one. We did one like that in our 10-6 notes. This is part of what your quiz is on Monday. All right. Now, if our intersection point lies right on the circle, like in number 3 and in number 4, so this time the secant line's intersecting a tangent line. Tangent line intersects the circle at exactly that one point, the intersection point. This one is the same as any other inscribed angle, that it's exactly half, like this angle right here is exactly half of its intercepted arc. Okay? So this one, though, is asking me for the measure of arc PSQ. So there's a couple ways we could tackle this. I personally just found this arc by doubling that angle. Okay, that'd be 156. Or you could set up this equation. If this equation confuses you, I don't have to do this. I know that angle is 1/2 the measure of its arc. We call this x. Times both sides by 2, you get 156. And since they intersect at that one point, what do the red arc and the blue arc have to total up to? 360. So then to find the blue, I could just do 360 minus 156. So the measure of arc PSQ is 204. Another way you could do this, and I'm curious if anyone did it this way, is you could find this angle since they're supplementary of each other, and then just double that. Did anybody do that? Got a couple people last hour who did that. Okay, that would work too. Did you also get 204? Yeah, that works. Number 4 is very, very similar to this one. So again, I'd probably just, hey, I know this one's 18, so double 18 is 236. Okay, because I know that measure is 1/2 of its intercepted arc. But again, they're asking me to find this arc over here, xy. So then I could just do 360 minus 118. And I got the measure of arc xy to be 124 degrees. Or, as I mentioned to the previous one, find its supplementary angle on the other side of that secant line and double that. You get 124 as well. That's our rule if the intersection point's on the circle. And then our third case scenario, intersection point is outside the circle, is that angle formed here by two tangent lines is 1/2 of the big arc that's formed minus the little arc that's formed. All right, so I know x is 1/2 big arc minus little arc. They don't tell me what little arc is, but did anybody find that? $94 is right. What'd you get? Not get 94. It's just 360 minus 266. If this is a tangent line, it's only intersecting at one point. So 360 minus 266 gives us 94 right there. Thanks, Matthew. So external, 1/2 big arc minus little arc. I got 86 degrees for that one. All right, this one, same thing. The only difference with this one is I know the angle that's formed, 64, and this one has a secant line and a tangent line, but the rule's the same if it intersects outside. It's 1/2 big arc, which is x, minus little arc, which is 39. Times both sides by 2. Add over 39. I got 167 degrees for x. Okay, so there's a little review over what we learned in 10.6. So your quiz on Monday is 10.5 and 10.6. I have a quiz review to give you at the end. All right, today we're still talking about like intersecting chords and secant and tangent lines, but instead of looking at the angle measures that form, we're going to look at the actual segment length because there's relationships with those as well. Okay, so now we're measuring the length, not the angles, not the arc measures. Now we're actually measuring like the lengths of the chords and the secant segments because we can't measure the length of a line because it goes on forever. Okay, so we'll get into all that. The geometry is just kind of more like rules. What's tough about this one is it's a lot of algebra review. Okay, so towards the end we got to review over a couple algebra skills. All right, so here's our first rule, first theorem. If you have two chords that intersect, the products of the lengths of each segment are equal to each other. All right, so if I have this chord, this segment length, AB, so the product of that segment length and this segment length, BC, is the same as the product of the other segment length. So this is my chord, DB times BE. That's always going to hold true. All right, so notice how these, since they're chords, they're obviously always going to intersect inside the circle, right? Because there's a different rule with secants and tangents when they intersect outside the circle. So let's try this one. So here I have this chord length. So its segment pieces are x and x plus 12. So I want to find their product. I'm going to times those in a minute. That's equal to this chord length segment products. So x plus 6 times x plus 2. All right, everybody with me? All right, let's review over how we multiply. Here I just distribute. Here I also distribute. Some people you might have heard like FOIL. I don't love that word. But he's just distributing. So I got to take x plus 6 times x plus 2. So I got to multiply and distribute the x through. So that gives me x squared plus 2x. And then I also have to distribute the 6 through. So plus 6x plus 12. All right, so here I have 8x. I'm going to go ahead and add those together. Now I want variables on both sides, so I'm going to try to group my variables together. And what do you notice about the x squareds when I go to move them to one side? They cancel out. Okay, that's nice. So I'm going to go ahead and move over this 8x then. So we get 4x equals 12, meaning x is 3. Okay. I'm going to try a couple of these like word problems. All right, biologists often examine organisms under microscopes. The circle represents the field of view under the microscope with a diameter of 2 millimeters. Determine the length of the organism, which you can see right there, if it is located 0.25 millimeters from the bottom of the field of view, round to the nearest hundredth. Alrighty, so we know this diameter, this whole length is 2. And we know this little length right here is at 0.25. So if this is a diameter, and this is a chord, when it intersects the chord, 2 things happen. We learned about this before. When a diameter or a radius intersects a chord, 2 things happen. Can somebody give me one of the things that happens? Gwen? Yep, it bisects it. So she's saying those 2 parts come congruent. That's exactly right. It bisects it. And something special with the angle they form.
The 90 degree.
They form, yep, they're perpendicular to each other or they form a right angle. Good. All right, so what we're trying to find is this length, right? So let's go ahead and call it x. And if that's x, this is also going to be x because the diameter bisects the chord. All right, so here I have a couple segments that are being split. So I have this is 0.25. What would this length be? Well, it would be 2 minus 0.25. So that red chunk is 1.75 millimeters. Okay, so let's take the product of those. Is equal to the product of the other 2 segments, x times x. What's x times x? X squared. Thank you, Matthew. This product is 0.4375. To solve this, I just got to square root both sides. And that would be that length x that we're trying to find, 0.66 millimeters, rounded to the nearest hundred. Oh, sorry, go ahead. I'm sorry. Okay. Sorry. You're just so intrigued by the lesson. Time flies when you're having fun in geometry, right, Cole? All right, try another one. Scientists unearthed part of a circular wall. They made the measurements shown in the figure. Based on the information in the figure, what is the radius of this circle? Round your answer to the nearest hundredth. Okay, so they're saying this forms a circle. And obviously, you're like, all right, this circle is going to be pretty big. If you kind of even just draw this out here to make a circle. And we only unearthed part of it. Okay, everybody kind of visualize that a little bit? All right. So my center would probably be somewhere about here. And we want to know the radius. All right, well, the measurements shown, we know that this piece had a height of 3. So that height is going to be directly perpendicular to this. So it's going to be part of this whole diameter. All right, now only this chunk is 3. I don't know what this chunk is. I'm going to call it x. This whole green chunk is x. But I know this chord that it's bisecting is 12 and 12. All right, so we can use this little theorem that the product of these segments So this one would be 3 times x is the same as the product of these segments, 12 times 12. All right, so I get 3x equals 144. So x is 48. But they just didn't ask me to find x. They want me to find the radius. Ideas of how we could do this. Malik?
48 plus 3 divided by 2.
Good. 48 plus 3 would give me the whole diameter, right? The diameter is 48 plus 3. So the diameter is 51 feet. And then he said divide that by 2 because I know my radius is just half my diameter. So divided by 2 or times by a half. Math is the same. 25 and a half feet. Good job, Noah. Okay, there's a couple of those. So as I mentioned before, our previous lessons, we've been measuring angles and arc measures made by tangent lines and secant lines. But if I want to measure the lengths of those lines, they have to be segments. They have to have endpoints. Otherwise, I can't measure the length of them, right? So here we just have a couple new vocab, but they're exactly what you guys already know. You know what tangent is, you know what secant is. Now they're just segments, so they have endpoints. All right? So a tangent segment is just a segment that has endpoints and it intersects the circle at exactly one point, and one of those points is its endpoint. So this right here, endpoint, and see how it intersects my circle at that one endpoint? That's just called, instead of a tangent line, because it doesn't go on forever, tangent segment. I'm going to go ahead and give this some labels. I'm going to go A, D. So as an example, segment AD is a tangent segment. All right, so a secant segment is the same as a secant line, intersects my circle at exactly 2 points, but it has endpoints. So it intersects it here, and one of the times it intersects the circle is the endpoint. So this whole segment that I highlighted in green, this is a secant segment. All right, so let's go ahead and call that C. A, C would be a secant segment. Just basically combining 2 vocab words that we already know how to do. All right, we know what external means. It means outside the circle. So an external segment is the piece of the secant segment that lies outside the circle. So this piece right here, I'll call this B. That red piece, this would be the external segment. AB. Okay, our next theorem used that vocab, so we just got to understand what that means. All right, here's our next theorem. So now notice the intersection point is outside the circle. Okay, before we had 2 chords, they intersected inside the circle, and we just found the product of the pieces to find the lengths. We're still doing lengths, nothing with angle measures. We already done that. So now this theorem says if they intersect outside the circle, the lengths of these pieces will be the entire secant segment, so AC, and the product of the external piece, so AB, that will be the same as the other secant segment. So this entire secant segment would be AE, the product of that, and the external piece, AD. Okay? Just unfortunately kind of like a rule you gotta memorize. So the entire secant length times the external piece is going to be the same as the entire secant length times the external piece. All right, so let's try one of these where the intersection point is way out here. So this blue secant segment, the external piece is 8, and then the chord length there from H to I is X. So what's the length of the entire secant segment? What'd you say? Careful. 8 plus X. We can't add those. X plus 8. They're not like terms. We can't add them. All right. And then I have this secant segment. This one's a little bit easier because the external piece is 10 and the chord piece is 24. So the whole thing, 10 plus 24 is 34. All right. So the reason why I need to find those is because to find the actual measurements, we take the entire secant length. So I'm going to start with the blue. The entire secant length times it to the external piece. I'm going to put the 8 in front. That product is the same as the other secant piece. So the entire secant length, 34, times the external piece of 10. Everybody understand where I'm getting these numbers? The whole piece times the external piece is the same as the whole piece times the external piece. All right, let's quickly solve this. That's all I need to find was x. Okay, that's our rule. Now the next theorem is really the same rule. They're just saying, hey, what if you have a secant segment and a tangent segment? And the only thing that's different with the tangent segment is it's all external piece. But the rule's still the same. You're still going to take the length of the whole thing, which is jk, times the external piece, which is jk. So it just ends up being this times this, is the same as the whole secant piece, jm, times the external piece, jl. Okay? So this time, the only thing different is tangent, the entire piece, times the external piece, and the whole piece is the external piece. So we just do jk squared, that times itself. If you want to write out this, you can. It's the same thing. That is the same as the entire secant piece, jm, times the external piece, jl. So it's really just the same rule, just looking at now the tangent piece. Okay, so let's try one of these. This is algebra you might not remember how to do. Okay, so we're going to go over it. Here's my secant piece. The external piece is x. The whole length of this, x plus 2, is 2x plus 2. With me? And then I have a tangent piece. All right. So let's start with the secant piece. It doesn't matter because it's an equation, which side you start with. So the whole piece, 2x plus 2, times the external piece, which is x. So I'm going to write the x in front here. It just makes it easier to distribute. I know that's the same as the length of the tangent piece, which is 12, times the external piece, which is 12, or 12 squared. However you want to do it. All right, here we go. 2x squared plus 2x. 12 squared is 144. In the previous example, we had x squareds on both sides and they dropped out. And then the other one, we had an x squared. Let me go back to that one. Oh, get past it. Here, I had x squared, but it was my only variable term, so I could just square root both sides. This equation's different. First question, can I add those together? No. Second question, can I square root both sides? You could try, but it's going to get ugly because you're going to have this x stuck underneath the radical. Okay? So this is what you learned last year, but you might not remember it. Okay? And we've done a couple like this. I've shown you this as a refresher. It's just been a while. So when this happens, this is called a quadratic equation because you have x squared and another x. We set these equal to 0. and we try and factor. Okay. If you don't know how to factor, you need to learn. So I'm going to show you a couple. There's some on your homework that you can practice. But if you really need help factoring, you need to come into RTI next week, and I will reteach it to you if you don't remember it, okay? First step, because in Algebra 2, guys, you need to know how to factor.
Yeah.
That's all we do.
Yeah. Everything. Like, everything.
First step when I factor is what?
What?
First step when I factor.
Take out.
Oh, is there a value of A?
No, before that. Take out what? You're about to say it.
Like your greatest common.
Check if there's a GCF, greatest common factor. Do these numbers have a number in common? 2. All right, so it's an equation. We're just going to divide both sides by 2, get rid of it. The reason why we do this is now we're working with smaller numbers. Then the way you factor depends on how many terms there are. Right now I have 3 terms. So what we do is we break this down into 2 binomials, because when you factor, you're just undoing distributive property. You're undoing multiplication, okay? So the way you kind of do this, and maybe once I start to talk through this, about half my class was like, oh, yeah, I remember that. The other half was like, never seen that before. And I know that's a lie, because this is like Algebra 101 here. All right, so I have x squared first. The only way I can multiply to x squared is x times x. Then you look at this number right here, which is negative 72. This is how I show my work. I'm not sure what you've been taught. So I find 2 numbers that multiply to 72, that have a product of 72, but when I add them, they give me this number in front of x, what's my number in front here? 1. So think of some ways to multiply to negative 72 in your head, and keep thinking of factors of 72 until you find ones that add to 1. Ben, you think you found this already?
Yeah.
What do you got?
9 and negative
Okay, let's try this. Guys, is 9 times negative 8, is their product negative 72?
8. Yeah.
Okay, good. Do they add to 1?
Yeah.
Good. So you found those. So that's what goes here. Plus 9 minus 8. This is called factoring. Do not write this down, but here's what we just did. Do not write this down. I don't want to confuse you. If I were to multiply this out, do you agree that we'd get this? You're just putting it back into factors. That's why it's called factoring. You're putting it back into its factored form, okay? Now, it does get a little bit more confusing if there's like a 2 here, because then it could be like 2x and x. But I think the ones in this class are usually just 1s in front here, which makes it a lot easier, okay? All right, now, the reason why we set this equal to 0 is now I have 2 factors whose product is 0. And in math, the only way I can get a product of 0 is if one of my factors is 0. Can you think of 2 numbers that multiply to 0 that neither of them are 0? No, it's impossible. There's no way. Okay? So you set up 2 little equations that, all right, this has to be 0 or this has to be 0. Giving me negative 9 and positive 8. And if you look back to your equation here, you can see why this works. 8 minus 8 is 0. That would make this product 0. Agree? This is called the zero product property. ZPP. Negative 9 plus 9, that would make that 0. We get a product of 0. Now, when we're looking at our diagram here, would it make sense that this external piece segment of x is negative 9 units long? No, so we ignore that one. 8 would be my answer. Since I know we struggle with some factoring, on the answer key on the worksheet, I put a little hint on which ones you need to factor. Hint, this one you need to factor. Hint, this one doesn't factor. Sometimes you're going to get quadratic equations that don't have these 2 numbers that multiply to this and add to this. Let's take a look at one of those. They don't factor. This I actually don't think you got to. They're doing it in Algebra 1 right now, this week. But nobody knew what I was talking about last hour. So I think you maybe just didn't get there last year because of COVID and stuff, I'm guessing. Okay? So I'm going to show this to you. So pay attention. All right, let's do the geometry first. Okay, you guys know how to do the geometry piece. So we have a secant segment external piece is x again. The entire segment piece is x plus 4, 2x plus 4. Tangent piece is 10. All right, so just like the last one, the entire secant piece times the external piece is equal to the entire tangent piece times the external piece, which is just itself, or 10 squared. I like to square it. All right. So we're going to have this set up here where I have this x squared and an x in my equation. I can't solve it by using square roots, and I can't combine like terms, so I set it equal to 0. I always try to factor first, because that's the quickest way to solve these. So I'd still go through my process of, is there a GCF I could take out right away? Again, I can divide everything by 2. You might not be able to, but if you can, it's easier to work with smaller numbers. And then you'd go through your process that I just kind of reviewed with you of finding 2 numbers that multiply to negative 50 and add to 2. And you might be sitting there for a while trying to find 2 numbers because there aren't 2 whole numbers that multiply to negative 50 and add to 2. So this one does not factor. Does not factor. What if they don't factor? In this case, we have some other options. Anybody know this? What I'm referring to? Yes. You could guess and check, but you'd be there for a while because they're not nice numbers. I like your thinking, though. Let me ask my Algebra 2 students in the back.
What?
If quadratic equations don't factor, how do we solve them? They don't factor. What? They don't factor. Other methods.
Give me an example.
Like this. How do we solve that? You guys know this.
You times the first.
No, it does not factor. We could complete the square.
Oh, yeah.
What else?
I'm drawing a blank.
You guys.
We're not your strongest.
I'm very
algebra
embarrassed.
We're not your strongest algebra 2 students.
You know this. If you literally did this on the last test. If it doesn't
I didn't do it
factor,
on that last
how do
one.
we solve it?
What?
How do we solve something that doesn't factor? A quadratic equation.
Oh, you just do a quadratic one.
Thank you! Oh my gosh! Oh, shoot, I taught you nothing. I'm gonna cry myself to sleep tonight. Thank you.
Did I know they're dreaming about?
Yeah, I had a dream about Sydney last night. All right. So we do something called the quadratic formula. Does that sound familiar to anybody?
A little bit.
Maybe you did do this last year. You did? There's a song that goes to it.
No, don't play the song.
Negative b plus or minus the square root of b squared minus 4ac over 2a.
And that's how you memorize it. Because it
works.
gets stuck in your head because it's a very annoying song.
Yes.
And one of my old students told me that they will, when they die, that song will be playing in their head. And I said, I cannot think of a better way to go. So you're welcome. All right, I already write this down. I put it up on Google Classroom, this big long formula. But basically, it's pretty cool. It's this formula where you just plug the numbers in to any quadratic equation you want, and it just, you crunch it in your calculator and you get the answers. Okay? So this is called the quadratic formula. You will use this in Algebra 2. I can prove to you where the formula comes from, but that's for another time. All right. It's x equals, and then draw a big fraction line like this. I used to make my Algebra 1 students like memorize this. You'll have to have it memorized next year, but we'll get there. All right, negative b, lowercase b, plus or minus the square root b squared minus the number 4, lowercase a, lowercase c, that product, all over 2 times a. Now it looks complicated, but it's not too bad. A, B, and C are talking about the coefficients from the equation. And it goes in alphabetical order. So A is the 1 in front of the x squared. What number's in front there? 1. So if I were to do this quadratic formula with mine, A is 1 in this specific example. B is the number in front of x. B is 2. And C starts with, or constant starts with C is your constant. C is negative 50. All right, so if I were to do the quadratic formula here, I would do x equals the opposite or negative b. B is 2. What's the opposite of 2? Negative 2 plus or minus the square root of b squared. So when I plug in b, I want to use parentheses. 2 squared minus 4 times a times c. A is 1, c is negative 50. All over 2, a is 1. All right, now you just use your calculator. Now it's just plug and chug from here. You plug the numbers in, you crunch that number, and those are your answers. Bless you. This would have worked on this one. We could have plugged this into the quadratic formula, a, b, and c, and we get out 8 and negative 9. Okay, it works on one. It works on every single one. That's why it's cool. This is how you start it, folks. You just don't type the square root in your calculator. Just punch in this piece. Okay, just do the part underneath the radical. 2 squared minus 4 times 1 times negative 50, and you get 240. Okay, don't type the radical yet. Just find that product. It's called the discriminant, the piece underneath the radical. What's 2 times 1? 2.
1, yes.
All right, so here's where we get our numbers. Pay attention. I know we're running a long time. Pay attention. This is important. In my calculator, I would have to do negative 2 plus the square root of 240. Divide that by 2. And I'd have to do a separate one, negative 2 minus the square root of 240. And divide that by 2. I'm going to show you. Let's start. I always start with the plus one. So I do negative 2 plus. Now you can type in the square root of 240, hit enter, divide that by 2. There's one answer. This is what I was saying. Like, we're not going to get nice numbers. We're just going to round this to 6.7. Wait. Was it 6.7 or 6.1? Oh, isn't it 204? Sorry, I did 240. 204 divided by 2. Sorry, it should be 6.1. My bad. Okay. Then to get my second answer, negative 2 minus the square root of 204. Enter. Divide that by 2. Negative 8.1. There are your two answers. Again, which one doesn't make sense? Negative. So 6.1 would be your answer. All right, as I mentioned, I'll show you one thing quick. On Google Classroom, I put the quadratic formula for you here. I made a note which ones you need to use the quadratic formula for, which ones factor, practice it. Again, if you don't know how to do this, you better get your tush in here. And then if you want to watch the song, it's right here.